to disperse protoplanetary disks, the observations that we have to constrain our theoretical understanding, as well as linking the dispersal of disks to the architecture of planetary systems. So I want to start by reminding you and myself which are the two most important observations on disk dispersals. We have seen already this figure a couple of times, and what it shows here on the y-axis is the fraction of optically thick dust disks as a function of the age of different star-forming regions. And what we infer from this type of data is that disks' lifetimes are a few or up to several million years if we change the scaling of the star-forming regions. There are also two interesting posters on the same issue to look at. Now, another question is, once the clearing process has started, how long does it take to disperse the disks? And to answer this question, we can look at figures like this one, where on the x-axis we have a diagnostic for the inner dust disk, and on the y-axis we have instead the total disk mass, which is measured through millimeter observations, and therefore it's tracing the outer dust disk. Now, here in green there are detections and millimeter wavelengths, and in red are upper limits. And what I want to drive your attention to is this intermediate region where we have optically thick inner disks, but we have a dearth or not that many disks that are detected at long wavelengths. So the statistics here suggest that the disk dispersal timescale are about 10 to the 5 years, so an order of magnitude shorter than disk lifetimes. Now, previous Protostar and Planets review chapters have done an excellent job in comparing different disk dispersal timescale, disk dispersal mechanisms, some of which are listed here on this slide. And they came to the conclusion that two of them, namely disk accretion and photoevaporation, are the dominant mechanism. So let me tell you a couple of words about these two mechanisms. Regarding viscous accretion, we heard a lot yesterday in the talk of Lesueur, and for now I want to bury all the dead bodies that he was discussing yesterday. So the thing I want to point out, it's only what is the expected evolution of the surface density as a function of radial distance from the star in the simple alpha viscous disk. And the point here is that it's relatively smooth as a function of time and radial distance. So another thing we need to look at for the disk dispersal process is the viscous time scale, which is shown here. And you see that is directly proportional to the radial distance from the star, so it takes longer to disperse the outer disk. And at the same time, for the conservation of angular momentum, the outer disk is expanding, and therefore it will take longer and longer to disperse the disk further out as the disk evolve. So it's clear that viscous evolution alone cannot explain the rapid disk dispersal timescales once the clearing has started. So that's why photoevaporation has been suggested as a possible mechanism. And here, this is a schematic view of photoevaporation from a previous Protostar and Planets chapter. And I want just to tell you what is the mechanism about. So here we have a star, a young star that has high energy photons. These high energy photons, in this case they were extreme UV photons, they heat and ionize the disk surface such that beyond a certain distance from the star, which is called in the literature gravitational radius, and is defined this way, the surface of the disk is hot enough that it escapes, is not anymore gravitationally bound, so it escapes in a thermal wind. And this is a relatively slow wind, as indicated here. Then between Protostar and Planets IV and Protostar and Planets V, it has been realized that actually photoevaporation doesn't start just beyond the gravitational radius, but well within. And that's why there is, in the literature, often described this parameter, which is called critical radius, and it's about a fifth of the gravitational radius. Now, to give you a sense of dimensions here, for a sun-like star, the gravitational radius would be around 9 astronomical units, and the critical radius would be 1.8 astronomical units. So you see that from a view in which photoevaporation was affecting the outer part of the disk beyond the location where even Jupiter forms, now we have winds that actually start within even the snow line. So now I want to show you what is the evolution of the surface density as a function of radial distance in a disk that is viscously evolving and photoevaporating. So just look at the solid black line, which is the total surface density. And what you are seeing so far is that the surface density declines smoothly with time, because at this point of time, the evolution is dominated by viscous accretion. But now you see that there starts to be a gap opening at this location, which is the critical radius, and now the disk is being cleared very fast because the outer disk cannot resupply the inner disk of material. There is this wind removing material. Then the inner disk is removed on a viscous time scale because it's accreting onto the central star, and the outer disk is instead photoevaporated very quickly because of direct ionization of the photons in the inner edge of the disk. So one thing I want to point out here is that photoevaporation is occurring throughout the disk evolution. It's not only when the disk is opening a gap, so there is more time for us observers to catch some of these photoevaporative flows, as I will show later in other slides. So what do I want to tell you that is new with respect to previous Protostars and Planets chapter? First of all, theorists have been great in developing a range of photoevaporative wind models, and I want to show you some of these, the flavors of these different wind models. Then I want to show you some new observations that can actually prove that photoevaporation is occurring and also test model predictions. I will discuss what are the implications of photoevaporation for planet, especially architectures. And I will conclude with what we think is the schematic picture of disk evolution that we put together for the review chapter. So I also want to mention that there are several other important topics that we discuss in the review chapter, and unfortunately I do not have time to present here, but I want to make a list of the most important ones and also point to some posters that you should look at. So the effect of cluster environments, external photoevaporation, tidal stripping, very important. And there are at least 3 posters that I found that are extremely interesting, so you should look at those. Then we heard yesterday about new models of MHD disk winds. We tried to discuss a bit the interplay between photoevaporative wind and MHD disk winds, but we have seen that some of these simulations are still need to be developed further, but they are extremely interesting. And then finally, in the chapter, we also point out that wherever we talk about disk evolution and also disk dispersal, we need to consider stellar mass dependencies as well as binaries, okay? And there are other 2 posters here that are very interesting. Now, let's start with the different flavors of photoevaporative winds. So the old one that was known already at PP4 is the one in which we have only extreme UV photons from the central star. This they can ionize hydrogen. So what we end up with is a surface of the disk that is fully ionized, is similar to an ultracompact H region, so it's very hot gas. In these models, you can define, as I said, the critical radius, which is the radius where most of the mass is lost, and it's inside the snow line. And another important parameter that I want to point out here is the mass loss rate, which is modest, is of the order of 10 to -10 solar masses per year. Okay, now since PP5, theorists have actually included other types of heating and ionizing photons. They have included X-rays as well as FUVs. And the point of this slide is just to show you that the penetration depth in terms of column of hydrogen that X-rays and FUV can penetrate is 1 or even 2 orders of magnitude higher than that of the EUV photons. And this has important implications for the mass loss rate, as you will see in the next 2 slides. So let's look at the models that include also X-ray irradiation, and they are listed here. So the X-ray layer is below the EUV layer, so it's mostly an atomic layer, and it's a bit cooler than the EUV layer. Now, when theorists, and here I'm referring in particular to Owen, Ercolano, and Katie Clark, this is the group have included radiative transfer as well as hydrodynamics in their model, they can compute mass loss rates, and these are of this order. So they are more than an order of magnitude higher than in the case of the EUV-only model. Then, if you then include also FUV photons, what happens is that you have another layer here that is mostly atomic. It's a bit cooler than the X-ray layers. And I should mention that both in the X-rays and FUV models, it's not possible to define just one critical radius from which most of the mass is lost. But again, the mass loss rate in the case of the FUV, it's very dependent on the total FUV luminosities, and Gorty and Hollebach have estimated a mass loss rate that is 2 orders of magnitude higher than in the case of the EUV-only model. Now, at this point, I want to say that all these different flavors of these queens, they can reproduce the 2 basic observations that I've shown you at the beginning. In other words, they can reproduce a disk lifetime of a few up to several million years, that depend also on the initial condition they put in, and the fast clearing after photoevaporation takes over viscous accretion. But there are quantitative differences between these models. So in the review chapter, we had quite some discussion on how we could show the differences. We end up with 2 plots. The first one is showing the normalized mass loss profile as a function of radial distance from the star. So what we see here in black is the EUV model. Most of the mass is lost at the critical radius. Then in red, it's a model that includes also X-rays, and X-rays are the dominant driver of photoevaporation. And you see that the mass loss is further out, and the peak is also broader. And then in the case of FUV, you see that there are actually 2 broad regions where mass is lost, one peaking around 5 astronomical units and one much further out. So this is a basic difference between these models. Then the other obvious difference is the total mass that is lost through the disk lifetime. And this is shown in a dashed line here. So you should look on this side of the y-axis. So the mass loss rates for X-rays and FUV are 1 or even 2 orders of magnitude higher than in the case of the EUV. So if you integrate then over the disk lifetime, the mass that is lost is of course 1 or even more orders of magnitude higher than in the case of the EUV only. Another difference, which is I think important for observers, is the evolution of the mass accretion rate as a function of time. And this is always normalized to the disk lifetime to better compare the models. This is shown in solid lines. So what you see here is that initially the mass accretion rate is decreasing smoothly with time. And this is because evolution is dominated by viscous accretion. But then at some point, the mass accretion rate declines very steeply. And this is where photoevaporation takes over viscous accretion. So the important thing to realize is that for X-rays and FUV, this drop in the mass accretion rate occurs much earlier than in the EUV case. And looking into the literature, we saw that the current mass accretion rate estimates are not detailed enough. They do not go down. There are not too much data at this location to really differentiate between these models, but I want to point to you a poster that is attempting to reanalyze a very large data set and trying to answer this question, even though I heard from the author that it doesn't have yet the answer. So these models, as I said, they are also quite they are very advanced, but they are also very complex. There is a lot of physics in there, and with that comes also uncertainties. And these uncertainties are reflected somewhat in the mass flow rates that I also reported before. So which are the main uncertainties in these models? Let's look first at the EUV model. Here, the main uncertainty is actually on the input parameters. We do not know what is the stellar EUV flux. We cannot measure that for young stars that are hundreds of parsec away from us. And even less, we know how much the disk is actually seeing of that EUV flux. So there have been some ideas on how to solve this problem. Alexander and collaborators have looked at the differential emission measure using FUV lines, and they ended up with this value for the EUV luminosities, but for a relatively narrow sample of, small sample of classical T Tauri stars. Then Herzeg has tried to extrapolate the EUV luminosity based on line modeling, including known X-ray and FUV properties, and this was done for a nearby object that is relatively well characterized at these wavelengths. And this is a number it came up, so a bit lower than what was estimated before. So recently, we actually proposed a new idea. We, first of all, calculated what is the free emission that an ionized or partially ionized disk surface can produce. We found that actually is measurable with current instruments. So we went back to the literature, and we looked in particular at this object, TW Hydra, which is a very known nearby star. And we found that if we look at long wavelength portion of the SED, there is one point at centimeter wavelengths that is higher than what you would expect from just thermal emission from dust. So what you can do actually is you can estimate the excess emission at these wavelengths, and you can calculate back, because we know the X-ray luminosity of TW Hydra, what is the EUV luminosity from the star. And we got values a bit lower than what Herzeg got, but they are not completely off. So this is an interesting possibility to further explore. And I want to point out that actually Owen and collaborators have also done now a calculation. This paper came out a couple of days ago on AstroPH. They find results that are similar to us, and they also have another object, another relatively well-known star, in which they can compute with this method EUV flux. Now, this is for the EUV models. What happens with the other models? So for X-rays and FUV, we know better the stellar X-rays and FUV through observations. But nevertheless, here, the models are actually sensitive to other disk properties, in particular to the dust properties. In the case of X-rays, there is some sensitivity on the settling of the disk. And in the case of the FUV, there is also sensitivity to the presence of pHs, how much pHs you have in your model. And so far, it has not been possible to couple the radiative transfer with the hydrodynamics, because the radiative transfer itself takes, it's very time-consuming. So it's clear that in addition to the development on the theoretical side, we do need observations to test model predictions. So what I want to start with are some, those I called direct detections of winds, basically. So here the direct evidence is detecting gas that is flowing from these layers at the proper velocities expected by these models. And theories have been great because they have provided observers with a range of possibilities that they can look at. And I want to start by showing you model predictions from what we think is the best diagnostic so far of photoevaporative winds. And this is the Neon 2 forbidden line at 12.8 micron. So what you see here on this panel is the expected emission, in this specific case for the EUV-only model. So the emission is up here. Here is the disk midplane. Now, this is the profile that you would expect if you see the disk edge on, and you can recognize that this is a Keplerian profile, so mainly bound gas in this configuration. Then imagine you would observe this disk with high spectral resolution, for instance, using V0 on the VLT, that has 10 km per second resolution, and this is the profile that you get by convolving the theoretical profile with the spectral resolution of your instrument. So now what I'm going to do is I'm going to change the disk inclination and show you how the profile should change as you get to lower viewing angle and you start to see more and more of this wind coming towards you. So here is 90 degrees, now we move to 60 degrees, and you can see some of the blue emission coming up. This is more pronounced when you go to 30 degrees, and of course, when you are face on, you really see the signature of the wind, which is a small blue shift with respect to the velocity of the star, which is around 6 km per second. Okay? So this is what the theory predicted, and I want to show you that actually we have a very good case for photoevaporation, and these are data that we acquired with Vizier in 2009 with Michael Sterzik. So the data are in black. You see here, the spectrum is in the stellocentric frame, so that's why here there is V0, and the line is blue shifted, as expected. On top of it, I also overplotted the model prediction for EUV-driven wind, and I want to point out that this model was made before the observations, and I think it's a pretty good match to the data. Then we acquired additional data on this source. We did different position angles for the slit. We got a similar result. The line is blue shifted by about 5 km per second. And in addition with this data, we could actually constrain the region where most of the emission is coming from. And we saw that the emission is coming from beyond the dust inner radius, which in this specific case is large because this object has a cavity, so it's probably around 4 AU. So it's concentrated between 4 AU and 10 astronomical unit. And this is again in agreement with model predictions. Now, I want to tell you that actually this is not the only good case for photoevaporative winds. There are several others. And this is from the work of Sacco and collaborators, which I luckily could also contribute to. So these objects with red stars are very good candidates for photoevaporative winds. They have profiles that are slightly blue shifted. And there is by now a good number of papers that are presenting a few other candidates, as well as are discussing how to discriminate between photoevaporative winds and an outflow from this line. Now, although the neon is a great tracer of photoevaporation, I think it has some limitations. In particular, you cannot use this line alone to determine the mass flow rate, which is actually what we want to determine observationally. And we thought to show this in the review with this figure. So here in black are the data that we acquired, and in red and blue are model predictions. For red, only the EUV case, and X-rays, and blue, also the X-ray case. Now, I would say that both models are a pretty good match to the data. The problem is that the mass loss rate that they predict is different by 2 orders of magnitude. And this is important. We want to know what is the right mass loss rate, because if you believe this result, then you would infer that TW Hydra is still in the phase in which its evolution is dominated by viscous accretion. But if you believe the other results, then photoevaporation has taken over viscous accretion, and the gap in this disk is formed by photoevaporation, probably. So we want to understand what's going on here. So to address this problem, actually, we thought that the way to do it is to try to see if there is any evidence of an atomic flow, which can be only produced by X-rays or FUV. So we went back to some old data, which I'm sure many of you are familiar with. This is the work of Artigan and collaborators in 1995. They showed this beautiful high-resolution optical spectra of a large sample of T Tauri stars in Taurus. And what they found is that there was always this low-velocity component present in the spectra. And typically, that component showed a blue shift of about 5 kilometers per second with respect to the stellar velocity. So Elisabeth Tarigliaco, who is working with me at the University of Arizona, she took the challenge to actually reanalyze all that data set, as well as new high-resolution spectra for a subsample of objects, and she came to very interesting conclusions, so please see her poster. I'm highlighting here only the 3 main results. First of all, she finds that the luminosity of the oxygen 1 in the low-velocity component is tightly correlated with the accretion luminosity. Now, we know from other studies that the accretion luminosity is tightly correlated with the FUV luminosity, so this implies that the low-velocity component of the oxygen 1 is tightly correlated with the FUV luminosity, the stellar FUV luminosity. Then we also found a low value of the 6,300 over 5577 over 6 orders of magnitude in accretion luminosity. And finally, when we could compare line profiles from different species, including the neon, we found that the oxygen 1, the neon, which is in black here, is typically more blue shifted. This is just one example. Is typically more blue shifted than the oxygen 1. So putting all these results together, we came to the conclusion that the oxygen 1 is likely tracing the layer heated by FUVs, where OH molecules are dissociated and you get the atomic oxygen, and it has an unbound component which implies that the mass loss rate is larger, typically, than 10 to the minus 10 solar masses per year, and it's actually pretty ubiquitous in young T Tauri stars. So this is, I think, a very interesting line of research where we are going to see more development, hopefully in the next few years, not in earlier than the next Protostars Planets review. Now, indirect observations are also very important, and because I don't have much time, I will focus on one specific group of objects that are interesting for this review, and these are the transitional disks. These, we heard already in other reviews, these are objects in which the spectral energy distribution lack emission at near-infrared and or mid-infrared fluxes with respect to the median spectral energy distribution of classical T Tauri stars. Licalcium-15 is an example of that. These objects are thought to be caught in the phase of clearing their inner disk, and in some cases it has been possible, like in this object, to image the source at millimeter wavelengths and see that indeed there is a cavity in the disk in this case, a lack of millimeter-sized grains. There will be much more in the next review talk about transitional disks, so I want to tell you more about this, but I want to point out two different categories which are relevant for disk dispersal. First of all, there is the category of non-accreting transitional disks. Okay? Some of the spectral energy distributions for this sample are shown here. This is the work of Cesa and collaborators. They found that these objects are about 10% of the pre-main sequence population. Their properties, which are very low excess emission at infrared wavelengths, very low dust mass, no accretion, are consistent with photoevaporation, and in particular with the EUV-driven photoevaporation. So this would represent the later stages of disk evolution. Now, there is another interesting group of transitional disks, and these are those that are still accreting. And Owen and collaborators have pointed out that in this group you can again distinguish two different subclasses. One is those transitional disks that have very large inner cavity and also large mass accretion rates. Those, they cannot be explained by photoevaporation. And you will hear later, I think, more than probably they are disks that are dynamically cleared. But you will see, I think, also that one planet is just not enough. You need more than that. The other subset of disks, this one, is actually can be explained by photoevaporation. In other words, the cavity that is cleared could be due to photoevaporation having taken over accretion just at the time, basically, that we observe. And TW Hydra is actually belonging to this group. I want to point out here a poster that is actually looking in detail at the mass accretion rate for this subsample and revising some of this work that has been published. So now that I've shown you that the theory has grown quite a lot in these last years, as well as we have observations of photoevaporative winds, I think it's time to think on the impact that photoevaporation can have on planet formation. There were a couple of interesting things pointed out in previous Protostars and Planets review chapters, like the fact that the dust-to-gas ratio is increasing because photoevaporative winds are removing volatiles primarily from the surface. There is also, in conjunction with that, also chemical enrichment. But here I want to focus on the most recent results that are on the affecting the architecture of planetary systems. So here we are looking at the case in which we have a disk that is viscously evolving, photoevaporating. We have a giant planet that is subject to type 2 migration and moving basically toward the star. So first of all, it has been recognized already, this is a paper by Alexander and Armitage, 2009, that the same disk models that can explain disk lifetimes and the evolution of mass accretion rates can also explain the location of observed giant planets. And this is shown, the observations are shown in black, solid lines, and the models are shown in red. In other words, the fact that we observe giant planets inside the snow line can be explained by formation outside the snow line, migration, and then stopping of these giant planets at the moment in which, for instance, photoevaporation takes over and disperses the disk. In addition to that, and of course there will be a very detailed talk later this week in which there will be additional mechanisms added to photoevaporation. But in these cases, the focus was on this specific dispersal mechanism. Another thing we have looked at is the dependence of, in the location of the giant planets with respect to the mass of these giant planets. So what you see here in gray are the radial velocity observations of single giant planets. And then in dotted lines, what you see are model predictions for giant planets in different mass bands. And what is found here is that especially in this range, you can see that there are preferential locations where giant planets get stopped, basically. They stop their migration. And this is a possible test that can be done once we gather better data on the exoplanets side. This basically type of work has been also found by others. There is an interesting poster that you should look at during the coffee break. And the most important message here from all these papers is that there is a kind of coupling between the disk evolution, the formation of the planet, the gap that the planet is producing, that is reducing the accretion onto the central star and can drive photoevaporation and the final disk clearing. Now, I want to show you this movie because in addition to being a pretty movie, it also shows that things get way more complicated once, instead of having just one giant planet, you put there a more realistic configuration where you can have 2 or maybe even 3 giant planets. What you may have noticed is that the 2 giant planets, they merge here. This is work by Möckel and Armitage. And you will see in the next part of the movie that there are asymmetric gaps opening around these planets. And again, here, the message is that the opening of these gaps can drive the final clearing of the disk, which you are going to see right now in this way, and therefore stopping planet migration. Now, as I promised, here is the schematic picture that we put together for the review on disk dispersal. So we think we have, of course, a stage in which evolution is dominated by viscous accretion. Nevertheless, even at this stage, there can be some photoevaporation, and maybe the oxygen 1 lines that we detect are actually tracing this neutral flow at the early stages. Then, after a lifetime of a few or up to several million years, the mass accretion rate has decreased such that photoevaporation can take over viscous accretion, and then we have the opening of a gap, and we put there a planet because, again, we want to emphasize the coupling between planet formation, the presence of a planet formation, and the disk clearing mechanism. At this stage, we still have matter, gas, close to the star that can accrete onto the central star. So this is maybe the stage of some of the accreting transitional disks that I've shown you before, including maybe TWI. And at this stage, we already start to see some of the ionized flow, for instance, in the neon line. Then finally, when the inner disk has been depleted completely by accretion, the direct ionization of the edge of the disk by high-energy photons quickly clears out the disk, and the planet gets stranded somewhere and is not falling onto the star. So that's good. So I just want to conclude here, maybe leave here the key points, because I know that there is a coffee break, and take questions at this point. Thank you.
Thank you, Ilaria. Okay, we have the time for questions, and let's start from the central row.
Yeah, so Doug Johnstone from the Joint Astronomy Center in Hilo. The last time I got to the microphone, I said I felt young. I now feel old. When Dave Hollenbach, Frank Schuh, and I started work on this in the early 90s, I would never have guessed where photoevaporation would go. At the time, we were dealing with high-mass stars, and it's just gone an amazing direction. The question I have is, when you talked about trying to figure out what the EUV flux was, you didn't mention at all anything about connecting it to the accretion luminosity. Is that now thought not to be the case and not necessary? Because when we were playing the game, we were really worried about how you actually got to the end state when the accretion was going down, and if that dropped the EUV.
I mean, I thought always about that, because, for instance, especially in the FUV model, that problem comes back again. It could be like a dog eating its tail, no? If most of the photoevaporation is occurring because of this extra FUV emission or UV emission due to accretion, then as soon as accretion goes down, you are going to basically lose the photoevaporation, and then the mechanism doesn't work. I think the observations that we have on the Neon 2, those are on the latest stages, so the objects are accreting at very low rate. They do suggest that there should be some chromospheric component, and that component could also come from X-rays, for instance. I still don't know that, but that's a very valid point, and we discussed that in the review chapter.
Left, please.
Matthew Bay. I was just wondering, when it comes to interpreting the observations, how can you distinguish between, when it comes to interpreting the observations, how can you distinguish between a photoevaporative-driven flow and perhaps an MHD-launched disk wind, which later on, for example, may even be ionized?
Yes, yes, this is something that we were worried too. So the point is that if you remember the talk of Sylvie Cabri, typically those velocities are higher. So if you look at the profile here, and this is, so here we are talking about 5 kilometers per second blue shifts. And if you want to go to such low velocities in their model, you have to go very far out from the disk. And I told you that the emission is constrained within 10 astronomical units. We know that. So I think this is actually a strong constraint. But I'm actually more, I'm very interested in the new development of the MHD disk winds. And I look forward to see what are the velocity profiles they come up with, because that will be interesting to test.
Let's go upstairs, left-hand side.
Yes, I'm Carla Baldovin from Vienna. So first I would like to thank you, Ilaria, for the very nice review. And I wanted to ask you to comment a little bit in the possibility of using another optical forbidden lines as tracers of photoevaporation. Because you know, in the paper of last year, we found a very nice match between neon 2 and optical, not only oxygen, but
the sulfur 2 and the nitrogen 2. Yes. Yeah, I was looking at that, and I think that is really the direction. So if we want to determine mass loss rate directly from observation, we definitely need more lines. One, I mean, the sample that you had was still relatively small, and there was some issue also with the inclination of the sources. Some were seen closer to edge-on, so you can mix up the outflow and the wind. But I really think that that is the direction for to determine the mass loss rate. Yeah.
Yes. Let's back to the center. Okay. Yeah.
Yeah, Günter Wuchtel, Corot at Tautenburg Observatory. You mentioned the consistency of the migration photoevaporation picture with the architecture of single planet hot Jupiter systems. You might know there are now very beautiful entire full ultra compact planetary systems provided by space missions with a strong taboo so far on the name here in this room. Can you imagine that these architectures of dynamically full systems of planets are consistent with the same paradigm of migration evaporation?
I mean, it depends on when the photoevaporation starts. I think this is a question that is going to be addressed. I know at least a group that is trying to look at the migration of giant planets as well as the terrestrial planets to see whether you can end up in some of the compact configurations that are seen. At the moment, I cannot comment on that. I didn't do the simulations, but it's an interesting point. And also, that's why I wanted to emphasize the link to the planets, because we have always in mind what are the observables there. So, yeah.
Okay, let's go upstairs, right-hand side.
Hello, Aurora Cecilia Aguilar from Madrid. I just wanted to point out, when I saw this nice plot where you have the accretion rate and this cutoff that you have, depending on the photoevaporation model you use, and you mentioned, oh, it would be nice to have some experimental results.
I have your plot.
There are some, actually.
You have them?
Yes.
Yeah, so because I have your, wait a moment, I have your paper here. Yeah, there you go.
Yeah, that one. Actually, this is what I wanted to mention, that we have a poster about it too.
Okay.
And what we were measuring there was accretion rates using U-band and H-alpha, trying to go as deep as possible and trying to constrain what you can detect, what you cannot detect. And what happens is this hole where you have pretty much nothing below 10 to the minus 9 solar masses per year seems to be real. So it seems like we are really banging there on some limit, some real limit that could be actually the photoevaporation limit you were talking about.
Yeah, I think my point is that we really need to fill out this region, which is the most important region. Yeah. This region needs to be filled out.
Yeah, so what I'm telling you is this hole is real. It's not that we cannot detect them. So we have either the
we just need to get
there or nothing down there.
I agree. No, I agree, but I think this part needs to be characterized a bit better because there is a lot of spread.
Yeah, and there is also the work of Ming Fang that you may want to consider, where we are also seeing that either objects are accreting at some 10 to the minus 9 or a bit less, or they are not accreting. So there is a real cutoff of accretion there.
Okay, back to center again.
Hi, this is Davide Fedele from Max Planck Institute in Garching. Going back on Doug's comment, first of all, when you switch off accretion, your FUV and EUV flux in low mass stars drops by order of magnitude. So you need to sustain your photoevaporating big wind with X-rays for your time scale. Then, although there have been attempts to look at the disk dissipation time scale in different stellar mass, the trend is that is simply always the same. We see all the disks around different stellar mass, evolving with the same time scale. But I
do not agree on that.
Well, the statistics so far is not large enough, but this is the trend, and the heating process is different. In air big stars is EUV, is UV. In low mass stars is X-rays. So there's one process that works always at the same in all of this, and this is viscous evolution. And so I have a problem with photoevaporation. And then also, how do you explain this upper limits down there with the photoevaporative wind?
No, but I mean, here we didn't look in detail. There could be, for instance, binarities here, binary stars, and therefore you disperse the disk in another way. I mean, I'm not saying that photoevaporation is the only mechanism here, but I'm saying that for single stars, it's a plausible mechanism, and we have data that show that these things happen. That's it. By the way, I think actually there is evidence that disk lifetimes are stellar mass dependent. And this is shown through infrared observations, statistics, the work of John Carpenter, for instance. So lower mass stars, they live longer. The disks, they live longer than higher mass stars.
Left-hand side, please.
Kathy Clark, Cambridge. Thanks for a very nice and very balanced review. Just getting to the Iliaria results, which I find really interesting. In the X-ray models, what we find is actually the mass loss rate is set up at the sonic point for the X-ray flow, which is well above the disk. And what James Owen has done is experimented with sort of mocking up FUV heating. And you modify the structure above the disk, and you'll modify the diagnostics and probably the O1 flux that you get out.
Okay.
But the actual mass loss rate is still determined up at high latitude. So if that's correct, then you can still sort of have your cake and eat it. You can maybe get the correlation that you see between the luminosity and the O1, but you don't have to worry that when the FUV luminosity goes away, you're not driving your wind, because you change the structure down near the disk. But if the X-rays are still bright, which we believe they are, they can continue. So just a...
No, I think the strongest test to the FUV X-ray debate are actually the line profiles. So if you would find in all the sources that the neon 2 is more blue shifted than the oxygen 1, that would favor, I think, the FUV. Elsewhere, it would favor the X-ray.
Okay. Back to center. Yep.
Yes, yes, very nice talk. And I'm not an expert at all of this subject, but I was just wondering, I liked your slide with the final slide with the 3 different phases.
There are jets there.
Yeah. That was not my comment.
No, actually, no, they are not there. But I was thinking about it,
Well, actually, you may want to add
we
the
should
magnetospheric injections and stellar winds in there, because we know they're there too. Yes. Well, so you may want to add that. But my question was about those stars that you show have large inner holes, but also large accretion rates, and you say they're dynamically clear. So where do they fit into this picture? The ones on top.
I don't know, maybe they formed the giant planets early on. I mean, there may be some photoevaporation, but the hole is primarily cleared dynamically, basically.
But then how do you explain, how do you explain that this inner region is not completely photoevaporated, and how come they can still accrete gas? How come that gas in the hole is not photoevaporated?
Yeah, I think you're right. I mean, these are a bit difficult. I don't know exactly these objects in particular. I think we would need really to study them more carefully. That's why I pointed out the poster before, because some of these accretion rates are going to change. Actually, I've seen already some of the results. It's not clear that...
I like your idea of saying that gap clearing by planets could induce the photoevaporation, but then these ones...
They do not seem to fit there. But I want to point out that actually also the other scenario, the dynamically clear disk, doesn't really fit much in our understanding of planet formation. I mean, you cannot just put one planet there. It seems like you have to put a full planetary system, and that's also strange. One thing that I think would be very interesting is to look at the statistics of giant planets detected at large separations, so for instance through direct imaging, and then at the statistics of this group of objects, because they would require giant planets at large distances. So you can basically check if there is some consistency there.
Thank you. Upstairs, on left-hand side and right.
Hello, Fabien Malbet from Grenoble. I saw that you don't have much constraints in the very inner regions, and I just want to point out that now we are starting to do imaging with interferometry, near-infrared interferometry of these regions. And for example, if there is a poster here in B16 where you could see the morphology of the inner regions and the region where you have the cavity, the beginning of the cavity, and the rest of the disk.
Dust or gas or both?
It's mainly dust.
Dust. Okay.
Yeah, it's a beautiful image. Yeah. So, okay, left-hand side.
Hello. Wait.
Yeah, I think so.
Hello.
Yeah.
Hi, this is Feng Tian from Tsinghua University, Beijing, China. Nice talk. I have a quick comment and a short question. The comment is that in the study of the highly expanded planetary atmospheres, very close to stars, so the hot Jupiters, it has been shown that if you use the assumption that all the photons are deposited at a single layer, then the calculated escape rate is can be off by orders of magnitude than if you do calculations considering detailed radiative transfer. So the question is, you mentioned that in the EUV model there's a critical layer assumption. What about the X-ray and FUV models? This is my misunderstanding that
yeah, sorry, I didn't mention that, but they do detailed radiative transfer.
Great. Yeah. So what about the EUV model? Do they do that too?
No, but that's much simpler, the problem, so I think there is not much of a need.
Thank you.
Okay, left hand side.
Hello?
Yeah.
Hi, Sergei Nayakshin from University of Leicester. This relates to a question about these mysterious sources that have relatively high accretion rates, and yet they are in transitional phase. So there is a new planet formation model that well, they're not on Friday yet, but hopefully it will be discussed a little bit. But in that model, young giant planets can be losing mass when they migrate too close to a star, so that tidally you disrupt some of the envelope. And I have a paper published this year where these sources are explained by, so the planet opens the gap, but then when it is tidally disrupted, material is accreted from the planet onto the star. So you can have a gap and yet the accretion onto the star at the same time. So I think that's a possible explanation for this.
So these large gaps?
Yeah.
Okay. Well, I will look at the paper.
Okay, thank you. Last one, very quickly. Yeah.
So I want to point out that on the monsters in the poster that Elizabeth, that Ilaria is showing, we are also checking if there are photoevaporation signatures with the lines, with the optical lines, the oxygen one, etc. So we have preliminary results, but we can discuss them in the poster. And I want to point out also that when we discuss about the not detection of accretion rates, we have to always keep in mind the observational biases and observational limits are different for different masses. So we should be careful that most of the targets with very high accretion rates are also very massive. So we should always remember this.
Thanks. Okay, let's thank the speaker again.